Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Peng and Diana Valencia with us today. Hello, Bo. Hello, Diana.
Hi,
Hello.
Francis. Hi, everyone.
Hi there. let's start with you. What's your geolocation? Where are you located at?
I'm in Toronto right now. I'm a graduate student, graduating student at University of Toronto, working with Diana.
Very cool. And how far along are you on your graduate student trajectory?
I'm actually defending in just a little bit more than a month, so I'm really close.
Well, let me be among the first to say congratulations, Dr. Peng. That's awesome.
Oh, that's very nice of you. Thank you so much.
You are welcome, but get used to it. Very cool. Very cool. And Diana, so you are also in the frozen tundra of the north.
So I'm actually not because I'm in a research leave. So I'm in the south of France. So that's why I was
Oh,
going for the
oh,
sun.
oh, I pity you. I pity you.
Yeah,
So
very privileged here.
are you around Nice, for example?
Exactly, exactly. I'm working with the folks at the Observatoire,
Ah,
Directeur.
yes, 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 yes. I have only visited Nice as a tourist, so but yeah, very cool. Yeah, it's very nice then. Very cool. All right. Let's see. And Bo, what do you like to do for research?
Yeah, so like the general idea is to combine a little bit of geochemistry and a little bit of planetary science. Uh, but the overall gist of my thesis is on the role of carbon during the formation of planets, and this paper is a little bit special in that I mostly deal with like exoplanet stuff, but solar system stuff. But this one is pure exoplanets, but still it's a lot of fun to do. Uh, yeah, so like basically I want to answer like how carbon gets depleted as it was delivered to terrestrial planets.
Cool.
Um, yeah.
Very nice. And Diana, what do you like to do for research?
So I was very lucky that when I was a grad student, the field of exoplanets was just starting. So there were a lot of questions that I could ask, and I focused
Uh,
on the small planets because they seemed really interesting. They're very complex. There's a lot of things that you cannot ignore, like what happens in the interior gets connected to the atmosphere, it gets connected to the observation. And so I really like those sorts of problems and just thinking about them with different tools and trying to go as simple as you can with a model without it being too simple.
too simple. Yeah. Very cool. Very nice. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Puffy Venuses, the mass radius impact of carbon-rich atmospheres on lava worlds. And Bo and Diana, take us away.
Right. So I'm this paper started the idea started I would say about 3 years ago, Bo. I think it was 3 years ago that we were discussing a few projects in a course, and one of them inspired by the fact that we have these planets that seem to be underdense compared to the typical terrestrial planets. And
Mhm.
they also seem very hot. So it was very difficult to just put hydrogen and helium on them. So they seem mysterious. And so one
Okay.
of the questions that I asked the students was if you what's the maximum size an atmosphere can have if it was mostly made out of carbon? So something like
Okay.
Venus, but can you extend it more and more? And I think that Bo liked the question and he won with it. And so this is a culmination of many months of hard work.
Mhm.
And we did get to that answer, and it was a really interesting answer because it wasn't clear if the atmosphere was going to be such that it would affect the structure of the planet. And so if you move on to figure two, just to give
Sure, let's
everyone a
slide
quick
on.
punchline.
Yeah, let's go to figure two and mass radius relationship. Radius.
Yeah, so
Okay.
so the punchline is that you can really extend the atmosphere of a planet in a way that you would measure the radius to be much bigger than expected. So not like Earth, where the atmosphere is tiny.
Right.
So the radius is mostly driven by by the rocky surface. These are planets. So this is the radius versus mass in the main figure. You see all these dots, those are planets with measured variables.
Hmm.
And the gray shaded area is where you would have rocky planets. And
Okay.
then the gray solid line is where you would line up all the planets if they would have the same composition as the Earth.
Okay.
But if on top of that composition you start putting carbon in the planet, and it will be divided in the mantle and in the atmosphere, you start extending the height of the atmosphere more and more, the more carbon you put, and then the hotter the planet is. So all those different lines, which I would like Bo, and he will do a great job at explaining in more detail, show how puffy those planets can be. And so even a planet like TOI 561b
Hmm.
that stands above the rocky region, that gray
Yeah.
region. So you would say it's not rocky. In fact, it could be rocky if it had enough carbon that you would have a very extended atmosphere, hence a puffy Venus. So with that, I would love for Bo to take it away because he was the one that did the heavy lifting of this work so that he can explain all the details that went into it to get this result and other ones that we found along the way.
Okay. Very cool. Nice. Bo, where shall we start?
Yeah, let's start in the intro a little bit,
Okay.
just to add a bit of context to this work.
Absolutely.
Uh,
Okay.
so, as Diana mentioned, the motivation is to explain the underdensity in some of the apparently rocky worlds that we saw, especially when they're very hot. But another like motivation is really the unknown sort of carbon abundances that exoplanets can have in general.
Hmm.
And we, like we don't have any direct measurements on the bulk sort of carbon abundances any exoplanets. Like for the Earth, we know that because we can, get gas from a volcano and like
Oh,
infer
yes.
how much of that is in the interior,
Hmm.
etc. But like exoplanet material, if you look at the polluted white dwarfs, that gives you actually a similar range of like carbon content as the
Okay.
amount
Okay.
that we have in solar system,
Hmm.
and that is still like a very large spread
Sure.
between something like
Cool.
100 parts per million to like 2-3% by weight,
Yeah.
which is quite a lot. Yeah, so
Very
yeah,
cool.
so that's yeah, so like we were thinking maybe besides explaining the underdensity, if like a planet is confirmed to be like this kind of lava worlds with thick carbon atmospheres, you can have like at least like some constraint on the bulk carbon content just by looking at their mass and radius.
Okay.
But that's kind of down the line, so we'll talk about that later. But let's get into the model a little bit, and if we can go to figure one,
Sure.
so
Okay.
quickly talk about the atmosphere.
Yeah, let's go
Um,
to figure one. Yeah, these look like atmospheres. There we go. Okay.
yes, all right. Yeah, so these are some like sort of sample atmosphere compositions and
Hmm.
structures. So if you look at 1D, the bottom right one, yeah, so
Yes.
that's
Uh-huh.
the temperature and pressure structures of the three sort of atmospheres that we're showing in A, B, and C. So the basic idea is that it's a semi-gray atmosphere model with convection when convection is warranted.
Okay.
The difference between these three A, B, and C.
Uh-huh.
So A and B has the same equilibrium temperature of 1500 degrees Kelvin,
Got
whereas
it.
C has like a higher equilibrium temperature.
Got it.
And also there's a chemical difference. So I think A has like a solar C to O ratio, whereas B has a more reduced composition. So the C to O is a bit higher than A, and you can see both have an impact on the deep atmosphere temperature. So
Yes.
the difference between A and B gives you sort of the difference that chemistry can cause,
Very good.
whereas the A and C is where like a little bit of more irradiation can cause. So we use this sort of radiative convective profile to capture something that previous like motion models
Most.
like well at least like some previous models haven't quite captured, which is like the deep radiative zone.
Okay.
And that's when when your basically energy budget is dominated by the star, and
It's radiant.
after you move down from the convective zone, which is like the middle part, you have this
Uh-huh.
deep part that's mostly isothermal, and that's where we're trying to capture there. And
Okay.
while
Okay.
so while solving for pressure and temperature, we also solve for the chemical equilibrium between like 6 species in the atmosphere,
Okay.
and that's shown in the sort of composition graphs in A, B, and C.
Yeah.
So we have like CO, CO2, H2, H2O, O2, and not shown here because it's not significant, but we also have CH4. Yeah. So
All right.
yeah, so that's like some very quick intro to the atmosphere model. Let's see, if
Wait,
you
yeah.
scroll down to,
Okay.
give me a sec,
Cool.
to equation 39, I can talk about a little bit about how the atmosphere is coupled with the interior. So that's
39?
on, yeah, so that's on page
Yep.
6.
Yep.
So while you do that, I'll just clarify something.
Hmm.
For these planets have an atmosphere in contact with the magma ocean. That would be the best scenario to have an extended atmosphere because it needs to be hot. And so at those temperatures,
Yes.
whatever mantle there is, it has to be liquid or partially molten at least. And so we're talking about that scenario, very hot planets with a magma ocean underneath their atmospheres.
Okay, so the irradiation from the star is a small component compared to the energy source of the planet itself. Is that true?
No, like the radiation of the star is still is dominating the energy
The upper
budget.
parts of the atmosphere. Yeah.
Yeah,
Okay.
yeah,
Okay.
and yeah, so like just by the high radiation that the planet receive, a lot of its mantle is molten. Basically,
Okay.
it's the regime that we're interested in.
Basically,
Yeah.
because it cannot cool more than what the atmosphere is allowing it to cool. So
Two.
it,
Yeah.
yeah.
Hmm.
I'm with you. Cool. Thank you. Okay.
Okay.
Equation 39.
Yeah. Yeah, okay. So this is basically a solubility relationship. So what this says is that, okay, now we know how much of, so for example, CO2 is at the surface of the magma ocean,
Okay.
and naturally it'll it'll dissolve into the magma ocean and reach a chemical equilibrium between the interior and the outside.
Yes.
And so this is like basically controlled by these Henry and solubility laws. So the more CO2 partial pressure you have just above the surface, the more of the carbon will be dissolved in the interior. Um,
Got it. Hmm.
yeah.
Yes.
So then you can sort of invert this entire system and say, okay, we have a total amount of carbon, and we use like chondritic amounts, so like the amounts typical to the solar system sort of building blocks, and say, okay, now let's distribute it between the atmosphere and the interior.
Okay.
And so we iteratively find atmospheric profiles, and then we find how much of carbon is buried in the interior as well. We add them together and see, okay, do we get to the amount that we want? And in
Cool.
the end, we can get to, distributing the amount that we want between the two reservoirs. So that's the main gist of this model.
Cool.
There's
Okay.
some sort of additional things I can point out, and if like you find them interesting, we can discuss further.
You just
So for example, we also have like a interior sort of pressure and temperature profile, and that determines how thick the magma motion is.
Oh,
So
right.
the hotter the surface is, the thicker the magma motion will be, because like as you go deeper into the mantle, the pressure becomes higher and the
Yes.
material tends to solidify.
Okay.
Yeah, so that determines that, and that determines how much of carbon, for example, you can bury into the interior.
Okay.
Okay, so with that, let's go into the results a bit. Let's look at figure 1.
Okay. So
Sorry, figure 2. Sorry.
figure two. So yep, we're back
Yes,
to
it's
this.
right there.
Good.
Yeah, so
Great.
okay, so figure 2a is really the main gist of the paper, as Diana mentioned. So the x-axis is mass and y-axis is radius. And we used like carbon and hydrogen content of ordinary chondrites and distribute them between
Okay.
these two reservoirs. And the orange like the different color lines represent different equilibrium temperatures or different insolation the planet gets.
Okay.
And so basically, the more insulation you get, the stronger like the deep atmosphere heating is, and the puffier the atmosphere you can get.
Okay.
So for a Earth mass planet like one, basically, you can get something like 30% of extra radius just by adding carbon.
Yeah.
That's the main takeaway.
Okay.
Um,
Cool.
and there's also like the shaded region, which is, as Diana mentioned, the possible sort of radii and mass combinations you can have by just varying how much of core and mantle there is in a planet without any atmosphere at all.
Okay.
So as you can see, in the low sort of mass regimes, something between like 4 Earth masses, like if we just add carbon, that can explain actually more puffiness than by varying the interior composition.
Okay.
Yeah, and we highlighted some planets with the little circles, and those are particularly both puffy and highly irradiated. We
Yeah.
think that those might be good candidates for our interior scenario.
Cool.
Yeah,
Very
yeah.
cool.
So that's part A, and if you look at part B,
Okay.
here we're basically varying the amount of carbon we have. So figure B, yeah. So the top
Yeah.
right one, yes.
Mhm.
Yes. So sort of different opacities of the lines, or like like the lightness of the lines to represent different sort of amount of carbon we have in bulk.
Okay.
And these are all like basically representative of sources of materials from the CI contrast, which is like it's like
Got it.
3% to bulk Earth, which is like 2 orders of magnitude lower.
Okay.
And it definitely has a strong impact how much of carbon there is in the atmosphere.
Mhm.
But if you compare that between the two different color lines, so the orange ones are 2000 degrees are more irradiated than the blue ones.
Uh-huh.
Yes. So
Yes.
2000 versus 1000 degrees Kelvin, you can see that equilibrium temperature still has like a very strong impact on how much of carbon, how much of extra atmosphere you get.
Cool.
So I would say that's like more dominating than how much of carbon you have. Yeah.
Nice.
So that's part B. Any questions, by the way? I don't
No,
know.
I'm following you. You're doing great. Good.
Okay, great. Okay, so if we look at part C,
Okay.
we're actually testing some different chemical scenarios. So the default one is we have chemical equilibrium at every level of the atmosphere.
Okay.
And if we only take chemical equilibrium at the surface of the atmosphere and assume the entire atmosphere is well mixed, so that it shares the same chemical composition,
Yes.
then we have the dash dot lines,
Got it.
and they actually predict actually larger atmospheres for the 2000 degrees Kelvin case.
Yes.
But if you only take CO2 and H2O and no chemistry at all, just these two gases,
Okay.
then you actually like underpredict how much of atmosphere you get.
No.
So that's saying that the thermochemistry of CO2 and H2O decomposition into CO and H2 and O2 is actually significant to in predicting how much of the atmosphere
I got
is,
it.
how large the atmosphere is.
I
So
got it.
the chemistry definitely matters. You won't get the same result by assuming like pure compositions.
Right.
Yeah.
Okay. Very cool.
Yeah.
Good.
So
I'm with you. Okay.
yeah, that's that. So
I
let's
would
go
just
to
like to add
yeah.
one thing,
Mhm.
just as another preview, is that we were really excited. We had submitted this paper. We were really excited when they got observations of 55 Cancri E, so you can see it in the main panel.
Mm-hmm.
Because it's one of the planets that we have as a community observed the most. It's really bizarre because the mass and the radius have been updated, and sometimes it can be rocky. Like you can see it here, that it sort of intersects the rocky shaded gray region,
Yes. Right
but
on.
not entirely. And sometimes
Mhm.
it's has some of the measurements have put it above, which means it has to have volatiles. So it was observed, and we were really excited when the JWC observations
Yes.
suggested that it could have an atmosphere of CO or CO2, which
Cool.
is exactly the scenario that we are proposing for 55 Cancri, and you can see there that this it can be an Earth-like planet with some CO or CO2 in its atmosphere. These
Yeah.
are this measurements, these observations need to be confirmed, but it made us really excited about the possibility of those worlds actually existing out
Mm-hmm. Mm-hmm. Because where there's two, there's many more.
there. Maybe.
Okay, very cool.
Yes.
Good.
Yeah. So let's move on to figure three.
It's going, oops, let me go the other way. Figure three. Let's see, these are the bulks. Those are your compositions of those BEs to CIs, folks. And the
Yes.
mantles, the volatiles, and partitioning functions. Yay. Okay, partial pressures.
Okay, yeah. So what this is trying to show is what happens if you have a mantle of different redox states, and that will
Okay.
control the C to O ratio of the atmosphere.
Uh-huh.
And that actually has a observable effect on the height of the atmosphere, which is shown in figure B, 3B.
Yes.
Yes. So
Yep.
if you look at the black line,
Yes.
that shows like quite a dramatic sort of increase of atmospheric height when C2O goes to somewhere close to 1. So
Yep.
the most reduced atmospheres, so the most like CO poor ones, would have like more like puffiness, or will be higher. And partially that's due to, like the blue line, which is showing you the bottom of the atmosphere's temperature. So the more
Okay.
reducing atmospheres tend to be also be hotter in the deep parts. And partially that's also due to the fact that, if your atmosphere is CO dominated rather than CO2 dominated, its mean molecular mass is also lower. So it also tend to be just like larger.
Yes. Yes.
Yeah.
Yes.
So if you look at
Okay.
3A, so
Okay.
that's the partial pressures at the surface for different C2O ratios.
Okay.
And as you can see, if we look at if we look at the dominating gases near the top, yeah. So as you go from the most reducing end near 1, so on the left here,
Uh-huh.
you're dominated by like a CO plus H2 atmosphere, and then you become
Yes.
when you add O, you like transition into CO2 atmospheres
Okay.
until like like CO2 would dominate at like something like 0.6, 0.5.
Yeah.
And like
Yes.
your CO would be more minor, and
Uh-huh.
we even extended the model to regions where O2 would become a sort of dominating gas,
Oh my
one of the
goodness. Yeah.
dominating gases. Yeah. So
Cool.
it is, like with the lack of knowledge for, the geochemistry of like rocky world interiors, we want to cover as much of the possibilities for mantle redox states as possible. And I think it is still possible to form, like extremely O2, oxygen-rich planets that actually produce, some atmospheres like this. And like another sort of, sorry, just to extend this slightly a little bit, is that another possibility is that the planet can form with H2O of ice or water, and the hydrogen can escape over time, and you're left with, like a unusually oxygen sort of enriched interior, and that will cause something that we see here. Yeah. So if you look at part C of the figure, that's the gas dissolved into the motion below, and the number one feature you see is that the red line, which is H2O,
Yeah.
as the dominating species, for what's buried in the interior. And that's also interesting because
Yes.
that's due to the fact that water is a lot more soluble than other carbon species. So when you both have carbon and hydrogen in like similar amounts, what you end up getting is mostly carbon in the outside and hydrogen in the inside. And so carbon is more, in this sense, more powerful in puffing up your atmosphere compared to hydrogen in this
Got
sense.
it.
Yeah, if you have like 10 times more hydrogen than
Yes.
carbon, then this might be a bit reversed. But here we're not in that region.
That's kind of an extreme ratio, but yes.
Yeah.
Yeah.
Yeah, so actually you can imagine, like having these, carbon dominated atmospheres and gradually adding hydrogen into it, and eventually it will become a sub-Neptune, right? So you can imagine sort of like a spectrum of carbon-dominated atmospheres on the one side and then sub-Neptune on the other side.
Right.
Yeah.
So
So
that
we're
yeah.
one end case scenario
Very cool.
that we're showing here.
All right.
Yeah.
Good.
So
Puffy
that's
Venuses. Puffy Venuses. Yes.
yeah. So that's our main results. We applied this to, as we said, 50 effect concrete E, and we can see that in figure 4.
Okay.
Uh-huh.
Alrighty, let's go to figure 3. I get the Puffy Venus's part. Let's go to an observation. There we go.
Yeah, so the stuff you saw earlier is mostly using one carbon and hydrogen content and varying sort of variables like temperature and C2O ratio.
Yes.
And for 50 concrete E, our default content doesn't quite explain the amount of like puffiness or like the underdensity it has. So, but we can get there with just adding basically more carbon. So, for example, if we look at the orange line, and that's when we assume a n-static chondrite like carbon content. So that's like something like 3 times more than our default carbon content, but still well within the range that solar system like bodies can have. And the difference between the dashed lines and the solid lines is assuming like 2 different C2O ratios. So like assuming different mental redox can give you the range of possible radii with the same carbon content for this one world, and that can encapsulate the measured mass and radius of this planet. So you can potentially use a solar system like carbon content to explain the actual radius that this planet has.
Cool.
Yeah. So that's that.
Cool.
So that's really yeah. Yeah, so that's really our main results. Like some more lines here, basically saying, okay, if you add even more carbon, you can get even larger, and
up here,
we don't even need to get to the most carbon-rich stuff in the solar system to explain what we have in 50 concrete E. So that's the main results. Diana,
I would like to add something, but maybe you can also discuss a little bit, is that it's not infinite. At some point, if you keep adding carbon, you're going to precipitate carbon from the atmosphere. So there's a limit to it. It's not that you can explain everything with carbon, just adding it. There is a limit to this. And so, and that's a good problem to have in the sense that it's predictable then. Then you know in which regime this model works and where beyond that, the planets would not be able to be explained with, carbon-rich atmospheres.
Exactly. Yes.
So can that maximum, presumably that maximum can be calculated, yeah?
Yes.
What is the maximum extent or the maximum amount of carbon you put in to get the maximum extent? Yes.
Yes. And that's something that we intend to do next. And what we did do for this work is to make sure that all our runs are beneath that maximum level. And that's actually what we did in figure 6 and equation 46.
Okay, let's go down. Figure 6 and Whoop, I'll get there. Sorry.
No.
Equation 46. There's 46, and then there's figure 6. Okay.
Yes, exactly. Yes. So, sorry. If you can look at equation 47.
Oh, that's right below it.
Yeah. So this is the equilibrium constant that describes the equilibrium between carbon, CO2, and O2. And so that's equation 47.
Can I just say that it's not being shared yet, Francis?
What?
Oh.
I don't see. Am I the only one that doesn't see the shared screen?
I'm seeing the share screen.
Oh, I don't see it.
We should be on.
Oh, I see it. Sorry. There, it's in another tab. Never mind.
No worries.
Oh, tab heaven. Okay. Yeah, we are. We're good to go. Sorry. Go ahead, Bo.
Yeah. So, okay. So, sorry. It's probably still easier to look at equation 46 first. So just the page.
We'll get them both on there. We'll get them both on there. How about that? Maybe not. Okay, 46. Graphite gas.
Yes. Yeah. So that's the equilibrium between graphite and O2 and CO2.
Yeah.
So basically, let's see how I explain this the best. So given one temperature, you can and like one O2 content,
Okay.
then you can imagine, like this equilibrium will fix the CO2 content,
Yes.
right?
Okay.
So
Okay.
if you have already reached that like CO2 partial pressure, and if you add more like carbon into the system, then that carbon will preferentially becomes graphite.
Okay.
But if you have a system with like some temperature and some oxygen content, but a CO2 content without below that level, then if you keep on adding C, that carbon will become like CO2 gas until that level is reached.
Until
So
second. Yes.
so an analogy for the other physicists out there who might not be super familiar is like basically this is similar with the saturation of water and the formation of clouds.
Yeah. Yeah. Very
So
good. Yeah.
So below below the partial pressure of the water vapor that condenses, you can add more water vapor until the like at this temperature the dew point is reached and you condense water vapor into clouds.
Cool.
So the sort of the closeness you are to condensation or to saturation
Yes.
is measured by this activity coefficient of graphite, which is shown in equation 47. Perfect. And that's AC here. So from our models, we can get
Okay.
FCO2 and FO2.
Yes.
And we also have chemical equilibrium just from basic thermodynamics, and then we can calculate A of C. And if A of C is below unity, below 1, then we're good. We're undersaturated. And that's what's shown in figure 6 here.
Cool.
So we calculated the A of C at the motion surface where FCO2
Base.
is the highest. And we see that consistently is below 1. So we're good there.
Oh, yeah. Definitely. Okay.
Yeah, but you can totally invert that question and say if we fix A of C at 1, what kind of CO2 amount do we predict and how much the atmosphere can possibly be? And that's something that we're going to do next. Yeah.
Okay.
Yeah. So that's the main results. So one more caveat I guess we can touch on is figure 5.
Okay. Figure 5. Let's see.
Yeah. So that's how we use parameterized opacities for the atmosphere, and that's parameterized with the measure profile of Venus atmosphere. And the reason for us to do that rather than using tabulative opacities is that there are many pairs of molecules whose collision-induced absorptions are not quite measured yet, so we don't have the complete pictures. So we're starting from something simpler. But of course, you can choose a different, opacity choices, and that will change how high the atmosphere is, because that will change how, how hot the interior is.
And so on.
Yes. And we will probe how much that can be different with the figure on the right here. So the z-axis is the the y-axis is the height of the atmosphere, and the different lines represent the different thermal opacities that we choose, and the x-axis is the ratio between the thermal opacity and the visible opacity. So the incoming light's opacity and the outgoing light's opacity.
Okay.
And so you see that yes, if we choose a lower opacity, then we have a smaller atmosphere. But this is not super sensitive to the opacity choices. We vary the opacity by like 20 times between the top line and the third line from top, and we get a factor of 2 difference. So it's not super sensitive. And also it's also not super sensitive to the ratio between the 2 opacities, which is the x-axis. And in fact, there's like a minimum if you vary the ratio. And that's because
50-ish, somewhere in there.
Yes. So so this ratio basically controls how cold the deep part of the atmosphere can be, or how hot that can be. And as you go to the right on this plot, the deeper part of the atmosphere will actually become colder, and that will shrink the atmosphere. But at some point, like the colder atmosphere will also be in contact with the shallower magma ocean. And
Yes.
so a smaller interior reservoir will push more carbon into the atmosphere, and so that will correct for this effect. So you
Okay.
can get infinitely smaller atmospheres. So that's like another thing that we tested. Yeah. So that's this paper basically.
Very
That's
cool.
the results. Yeah.
Very, very cool. Beautiful. Nice work.
Thanks.
Thank you.
Very nice work. Yeah. And Bo and Diana, I want to thank you so much for walking us through your very awesome article. And we kind of touched on it a little bit there at various points as we went on through. So let me go ahead and push on that a little bit. And where do you think we go from here, given the published article? Well, there's always additional models to run. But are there JWST campaigns, for example, to maybe narrow the uncertainties on the two that were on the plot right now, or other candidates? So are there other, I guess what I'm asking is, there other observational campaigns to find more lava worlds, exo-Venuses? And is there any laboratory astrophysics work that could be done that would help things like improving the opacities, improving saturations, so the input physics that goes into it? So where do we go from here?
Go ahead, Bo.
Excellent.
I'll finish, but I'll let you
Sounds great.
start.
Yeah, so both Diana and I are in this JVST group that have actually already taken phase curve observations of TOI 561b.
Okay.
So if you remember, that's one of the prime candidates really of this scenario.
Uh-huh.
Yeah, so like the obvious sort of next step for this model, which is like ongoing right now, is to combine it with a state-of-the-art interior model that we also have in our group.
Okay.
And so we can probe sort of the degeneracy between having a carbon-rich atmosphere, thick carbon-rich atmosphere, versus not having the atmosphere, but having a smaller core, so more mantle, like less dense material than, yeah. So like the gray region, if you remember that you saw in the mass radius diagram, that can be combined with
Yeah,
what
man.
we have here.
Okay.
Yeah.
Cool.
So that's something that we're hoping to do for this planet in particular. Yeah. So in terms of laboratory improvement, there are many things that can be done. So like we've been assuming a sort of clear-cut boundary between the atmosphere above and the interior, the rocky interior below,
Yes.
right? And we know that there's this rock vapor, rising into the atmosphere and get
Good.
admixed with the atmosphere,
Mhm.
and at some point that the atmosphere is supercritical, and the rock itself can also get to a supercritical state at high temperatures. So the actual conditions at the interface between the magma ocean and
Boundary
the
condition.
atmosphere can be quite bizarre. It can be quite interesting to look into. So that's something that we're hoping, both experimental work and also like ab initio computational sort of simulations can help shed light on. So like the sort of what is this combined fluids equation of state, for example, and how
Yes.
does it behave?
Yes.
Yeah, and more interestingly, can it be transported to the top? And so we see like a signature of the interior more directly than just just the gas species that we have.
Cool.
Yeah, so those are exciting things to think about. And of course, as we talked earlier, like better measurements for opacities at like higher pressures and temperatures for like basically everything outside of hydrogen and helium would be great.
Yes.
Yeah, and
That's
yeah, and like like increased catalogs of polluted white dwarfs can also shed some light on what we have here. Yeah,
I hadn't made that connection before, but yeah, good. Mhm.
yeah, because we were talking about the bulk composition, right? So
Yeah, yeah,
that's
yeah, yeah.
yeah, yeah. That's
See.
off the top of my head. That's what I think might be interesting. Diana, do you have anything you want to
Yeah,
add?
so I think you did a great job. I would just like to zoom out a little more. So this Puffy Venus scenario is in the category of hot planets, so maybe ultra short period planets. With our they're much easier to observe than colder planets. So that's exciting. Do they exist out there,
Mhm.
or are they explained by something else? So, as Bo mentioned, we cannot talk about the results of 2I-561 because we're not ready to discuss anything so far. But that kind of observations, exactly, is what we need in general to understand these planets. And I like to make a little ad for people when if they're deciding on JWST what to do, understanding these lava worlds is really important to understanding the Earth in its early
Yeah.
days.
Yes.
So in a
Yes.
different parameter
Yes.
space, etc. But these are really good windows to understand even our own origins.
Exactly.
So I think that's perhaps from the observational side, and then one theme that have always interested me since ever I saw a figure, Ed Bergen, showing the carbon depletion as a function of semi-major axis,
Okay.
is
In
really
the solar
trying to
system.
understand
Yeah.
why do we have the amount of carbon we have? And so and
I-
Bo really took that and owned it, this question. But in general, because some of the things we know as well is that too much carbon is bad. Too little carbon is bad because we need a stable climate, etc. But too much carbon is also bad. So kind of just zooming out and understanding what cr- what control the sort of volatile budget that the Earth has, I think is really important to understanding habitability.
Mhm.
Hmm.
Yes. Yes. Exactly. Very cool. Very good.
Yeah.
Well, I think it'll be really exciting over the next couple of years to see this field develop, and hopefully we find many more lava exovenuses.
See.
Very cool. So, Bo, Dr. Peng, and Diana, thank you so much once again for walking us through your very lovely article.
Thank you for
Thanks for
having
having
us.
us.
And that will do, everyone. And I hope this made your exovenus day, your astronomy day, just a little bit better. And we will see you on the next one. Bye
See you.
bye.